Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 4.2.1, which is the sine and cosine ratio. So we will be revisiting our good old buddy trigonometry. In the last episode of this, we learned about tangent, but we will be learning about his buddies sine and cosine today. In 4-56, they talk about the streets of San Francisco, where Juanisha is climbing up the street steps. And one of the steepest, Filbert Street, has a slope angle of 17.5 degrees, according to her guidebook. And once Juanisha finishes walking the 100 feet up the hill, she wants to know how high up she has climbed. So she draws a diagram to represent the situation. So it says, can the tangent ratio, which is what we have learned, be used to solve for the delta y? Why or why not? And so right now, if we know that the angle is 17.5 degrees, and she climbed a slanted distance of 100 feet, can we solve for her elevated distance? I don't think so, because right now tangent can only solve for the opposite and the adjacent sides, and so we couldn't even solve for delta x if we wanted to, given the tools that we have right now. So the point of this chapter is to determine what tools we're going to use in order to solve for the delta y and the delta x. In 4-57, we're going to find out how high Juanisha climbed in 4-56. But in order to do this, we're going to need to determine the relationship of the triangles at the right side. What it's asking us to do is it's asking us to use two different strategies to determine delta y of the slope triangles in the diagram at the right. So in this diagram at the right, I'll go and redraw the triangles twice. And so from here, not exactly 90 degrees, but I think we get the idea. So I'm going to call this a 1. I'm going to call this a 2. I'm going to call them delta y1. And then I'm going to call this 3 and 6. I'm going to call them delta y2. Now from here, given the fact that they're both 60 degrees because they exist on the same slope angle, the first way I can go and solve this is I could use tangent, right? I could say tangent of 60 is equal to delta y1 over 1. And so if I do tangent of 60 degrees, I'm going to get, now if I put it in exact form, I'm going to end up getting the square root of 3. But if I actually do the square root of 3 in your calculator, I'm going to get 1.7 something or other. Let me just double check that. 1.73205. I'll go and leave it as the square root of 3 for now. Go ahead and leave it as a decimal, whatever is your thing. Now on this one, I could do the same thing. I could say that tangent of 60 is equal to delta y2 over 3. Multiply this guy over, so 3 times tangent of 60 is equal to delta y2. Now I'm going to stop right here and put this in and leave it in calculator ready form, because check it out. This delta y1 is tangent of 60. And the delta y2 is 3 times tangent of 60. Notice the scale factor of these triangles. The scale factor is, in fact, 3. So it makes sense that whatever delta y1 is, I would take that value and multiply it by 3. So I could call him 3 times rad 3. Or, if I was to put it in a calculator, that would be 5.196 if I really wanted a decimal. The other way you could have done it is you actually could have done the Pythagorean Theorem on them. And so you could have done 1 squared. So 1 squared plus delta y1 squared equals 2 squared. You would get 1 plus delta y1 squared equals 4. And then subtracting 1 from either side, you would get delta y1 squared equals 3. And square rooting them, you would get delta y1 equals rad 3. Hey, I feel like we had that before. And then, of course, scale factor it up for the second triangle. Now, it says, calculate the ratio of the delta x over the hypotenuse for each triangle. Why must these ratios be equal? So, oops, that's A. So I did A over here on the right side. So I'm going to do B here on the left side. It's a little backwards, but I think we can handle that. If I do delta x over hypotenuse, delta x over hypotenuse, I'll go and abbreviate that as HYP. Delta x over hypotenuse for this triangle here is going to be 1 over 2, right? It's just going to be the 1 over the 2. And then in my second triangle, delta x over hypotenuse is going to be 3 over 6, which is equal to 1/2. So why are these the same? Why should they be the same? Well, they're the same because the triangles are similar, right? So when we write that down, they are equal because the triangles are similar. So the scale factor would ultimately reduce into the same thing. So now what they want me to do is they want me to use this knowledge here to solve for the side lengths of BC and AC in the triangle below, and we got to show all the work. So from here, let me go and just expand out their diagram real quick here. So they're giving me a triangle with a hypotenuse of 7, with this angle being 60. And with BC, I'll go and call him X. With AC, I'll go and call him Y. And so now what I'm going to do is I'm going to compare him to the triangle that I have that's most reduced, which is going to be my 1, 2, and rad 3, or 1, rad 3, 2 triangle here. So that's 60 here, the 1, rad 3, and the 2. Again, it's this triangle here that I'm referencing. And I'll go and just use similar triangles on this thing. So what I'll do is I'll say, well, what is my scale factor? My scale factor is that I have to multiply 2 by something to get 7. So I can say 2 over 7 is equal to 1 over x. I'm just comparing corresponding sides. So I can say that 2x is equal to 7. So x should equal 7 over 2, which means the length of BC is 7 over 2. I'll go and do the same thing to solve for AC. So I'll say that 7 over 2 is equal to y over rad 3. So here we go. So 7 rad 3 is equal to 2y, divide by 2, and what I get is 7 rad 3 over 2 is equal to y, and that's what this guy is. So again, it's this whole notion of similar triangles coming back to solve for missing sides of these right triangles. But eventually, in the next problem, we're going to learn of a ratio that allows us to use our calculators to get that similar triangle off the cuff. So I'll be right back with that problem. In 4-58, they introduced 2 new trig ratios with you. They say that in 4-57, you used a ratio that included the hypotenuse of triangle ABC. There are several ratios you might have used. One of these ratios is known as sine, and people abbreviate this thing as SIN, but it's pronounced as sine. And so for the triangle shown at the right, they're saying that sine of 60 degrees is rad 3 divided by 2. And that is because the sine ratio is what we call the ratio of the opposite side over the hypotenuse. And then it says another ratio comparing the length of the side adjacent, which means next to the angle, and the length of the hypotenuse is called the cosine ratio, abbreviated COS. And so let's go and write that down. Cosine is the ratio of the adjacent over hypotenuse. And so it says, like the tangent ratio, your calculator can give you both sine and cosine for any angle. Locate the sine and cos buttons in your calculator and use them to determine sine and cosine of 60 degrees. And it does. It gives you 1/2 for cosine and 0.866 for sine. And your calculator does give you the correct ratios as long as you're operating in degrees. So now it says use a trig ratio to write an equation and solve for a in the diagram below. Does this require sine or cosine? Well, I'm looking at part B here, and this angle is 23 degrees. I have a side that is opposite the 23 and a hypotenuse. So when I see that relationship, side, opposite, and hypotenuse with an angle, automatically I'm going to default to sine. So sine of 23 is going to equal, again, opposite, which is a, over hypotenuse, which is 15. So it's just like tangent, except not. So from here, I'm going to go ahead and multiply both sides by 15. I got to get that a by itself. So a is equal to 15 times sine of 23 degrees. So this would be the exact form, or some people call it calculator ready. if I'm going to figure this out in the calculator, I'm going to go and take sine of 23 degrees, and then I'm going to multiply it by 15, and I'm going to get 5.860. And that is a 5 right there. 5.860. So an equation for part C here, again, I've got an angle, I've got a side that's adjacent, and a hypotenuse. So then that tells me I'm going to be using cosine. So cosine of 37 is going to equal adjacent, which is b, over hypotenuse, which is 8. So that's going to give me multiplication of 8 on either side. So 8 times cosine of 37 is equal to b. And again, that's my exact or calculator ready form. If I wanted to figure out what that was, I would do cosine of 37 in a calculator and multiply it by 8. And what I get is 6.389 as a decimal. So there is sine and cosine. I'll be right back with the next problem. Let's revisit our old pal Juanisha to see if we can help her find out how high up she climbed. So because we're trying to find out just how high she climbed and not how far laterally she moved, that means that I'm going to be solving only for delta y. And again, what am I given? I'm given an angle, a delta y, which is opposite of that angle, and a hypotenuse. So angle, opposite, hypotenuse, that screams sine. Sine of 17.5 degrees is going to equal opposite over hypotenuse. So delta y over 100. I'm going to multiply both sides by 100. And I'm going to get delta y equals 100 times sine of 17.5. So let's find out what that is. Sine of 17.5 times 100. Looks like that's going to be delta y is equal to 30.070. 30.070 feet. And there you have it. I'll leave you with this question before I move on to the next problem. If I wanted to find out how far laterally she traveled, which trig operation would I use? I'll be back with the next problem. And here we are with the last problem. Hopefully at this point in time you have thought about which trig function you would have used to determine Juanisha's lateral motion. That would have been none other than cosine, because that delta x is adjacent to the 17.5 degrees. But if you didn't get it, it's not a big deal. We will have plenty of practice with these next 6 problems where we determine what trig function we're going to use to solve for the missing side. And so if we look at part A right here, I see an angle, I see a side adjacent, I see a side that's the hypotenuse. That automatically leads me to think cosine is my tool. So I'm going to say that cosine of 17 degrees is equal to adjacent over hypotenuse. What does that look like? That's 3 over x. And now I'm going to go and solve that equation. This is just like tangent, right? I'm just going to multiply both sides by x, and I'm going to get x times cosine of 17 is equal to 3. So I'm going to get x equaling 3 over cosine 17. I was trying not to impede on this guy's territory, but I think it's inevitable. Which ultimately ends up becoming x equaling approximately 3.137. And that's the answer to A. So exact form here, decimal form underneath. In B, again, I see an angle, an opposite side from the angle, and a hypotenuse. So that tells me that I'm dealing with sine, right? So this is going to be sine of 25 is going to be equal to x over 9. Again, opposite over hypotenuse. How do I get x by itself? I'm going to multiply both sides by 9, so this one shouldn't be too bad. X is equal to 9 times sine of 25, which then we will multiply out to become 3.80. Again, calculator ready or exact up top, decimal on the bottom. Okay, now this one here, C, you can totally use a calculator if you wanted to. First off, let's go and identify the relationship. I am seeing a 45 degrees with an opposite side and an adjacent side. This is bringing us back a little bit, hearkening back to chapter 3 here, where what we dealt with was tangent. So you could say that tangent of 45 is equal to x over 5. Multiply both sides by 5, and if you calculate tangent of 45 in a calculator, you will get it to be 1, which means x equals simply 5. Now, you could have done this one without a calculator, right? Because we've talked about 45 degrees having a slope angle of, or a slope ratio of 1. And so the slope ratio of 1 produces a slope angle of 45 degrees, so this one didn't even really need a calculator. Let's go and take care of the one on bottom here, D. Again, from the angle's perspective, this 62, I've got an opposite side, I've got an adjacent side. This looks like tangent again. So tangent of 62 is going to be opposite over adjacent, so 5 over x. Multiply x on either side, so x tan 62 is equal to 5. Divide both sides by tangent of 62, so x is going to equal 5 over tan 62. And if we put that into the calculator, we're going to end up getting 2.66 as the answer. 34 degrees, opposite of the 34 degrees, hypotenuse. Angle, opposite, hypotenuse. I am thinking that sine is going to be our weapon of choice, because that's going to be sine of 34 is going to equal opposite, which is 13, over hypotenuse, which is x. So multiply the x's on either side. Again, it seems like it's kind of the same thing, right? Just making sure that we identify the relationship that exists between the angles and the sides. So x equals 13 over sine 34. And then when you decimalize that, you will get 23.25. And the last question here, we got an angle, adjacent, hypotenuse, cosine of 20 is equal to adjacent, which is x over 10. Multiply both sides by 10. So you get 10 times cos 20 is equal to x. Punch that dude into the calculator, you're going to end up getting 9.40. And there you have it. There are your two new trig ratios, your two new trig relationships. As always, please leave comments or questions in the comments area, and I will see you all in the next episode.